Hey everyone, we are Team 13 and this is our interim presentation on analysis and redesign of a commercial blender. To start things off, this is a general overview of the topics that we'll be covering during this presentation, and we will start with the product description. A blender is a household kitchen appliance that is meant for daily use to mix, blend, and chop foods to make foods such as shakes, smoothies, or purees. The features that blenders include are high-speed rotating blades and speed controlled by electronics. The specific blender that we are looking at is the Oster Pro 1200 blender, which retails for around $90 and is produced at around 100,000 units a year. The customer base that we are looking at in terms of primary customers is anyone that is using the product for personal and daily use. They'll be using this blender to make smoothies, frozen drinks, and process larger foods, and this must be a tool that is easy to use and clean in household kitchens. In terms of secondary customers, we're looking at restaurants and cafes that will make larger batches of drinks and potentially baked goods, and this must be a tool that is easy to use and clean in commercial kitchens. In terms of functional analysis, we have come up with a fast diagram that outlines the primary function of a blender, which is to blend food, and the secondary functions such as mixing ingredients, storing food, assuring dependability, assuring convenience, enhancing the product, and pleasing the senses. How these secondary functions are met are outlined on the right here.
So here we can see the exploded view assembly of the blender that we're looking at. In total, we have 17 parts. The motor assembly and the PCB assemblies are each considered one part for simplification, as well as the fact that we can't optimize them in this manufacturing analysis. So in these figures on the right-hand side, we can see the jar assembly exploded view and the base assembly exploded view. We have the assembly sequence analysis as shown here, with the left-hand tree being the bottom-up assembly, where we begin from the bottom housing and make our way up with the assembly to form the blender assembly. And on the right-hand side, we can see the top-down assembly, where we start with the filler cap and lid and make our way down, adding components to create the full blender assembly. We compared both sequences, and as you can see here, we rank them accordingly with these qualitative categories. And we have 3 as the highest and 1 as the lowest. And as you can see here, sequence number 1 was the highest winning sequence.
Here's our function component mapping matrix. You can see each function is taken from the fast diagram and listed against each component in the assembly. Each component has a function that is mapped to, and note there is no function that is mapped by more than 40% of the components in accordance with the DfM guidelines established in LACTIC. This is our bill of materials for the Oster blender. The bill of materials shows the high-level assemblies as well as the individual components. The materials, assembly, and manufacturing processes are determined, and the costs are determined using estimates from lecture material and online cost calculators. Our rough estimates and vary based on what calculator you use. Please note that the total cost coming up to $55.8 is 60% of the total retail cost at $90. This is our quad chart for FM/DFA. It is used to determine what parts we consider redesigning, and this determination is made by ranking each component by functional importance, low or high, manufacturing assembly cost, low or high. The items in red are parts that we should consider redesigning using DfM/A guidelines and will be discussed later on the presentation. Please note that the motor assembly and the PCB are not in the scope of the course for redesign.
These two tables outline the commonalities and differences between our two consumer bases. So between household and commercial groups, both use a blender to mix the ingredients, break down the components, and pretty much contain whatever they're mixing. However, between the two groups, one group, the commercial side of things, manages much larger volumes of drinks, as well as different mixing speeds, and there's also different needs for maybe mixing versus completely chopping. And between the components, you can see that the base motor stays the same between the two groups, while the modules that we've designed accommodates the different needs of these two groups. So on the left here, we have the first jar, which is designed for household uses. It can hold a couple drinks. However, as you can see with the second variant, this one, which is meant for commercial uses, can accommodate much larger volumes, and it can also be used as a mixing bowl. And when these jars attach to the base of the blender, you can see that the top two components, 11 and 12, remain fixed to the jar, while components 8 and 9 remain fixed to the base. And 9 keys into 12 and ensures that the blades of the jar for each jar spin smoothly.
Another product family design will be the type of blender mixers. The first mixer is the original blades used to blend and mix drinks. The second variant removes the blades with a tool that will serve to mix solids such as dough. The third variant expands on the first design by increasing the number of blades to accommodate for larger volume. As mentioned in the previous slide, the product will incorporate different blades and mixing tools. The common interface of the different variants will include a slinger, drive, stud, agitator base, and a gasket. These will be used to connect the different variants of mixing tools to the entire blender base. Here is an assembly diagram of the original product with different variants without accounting for product differentiation delay. As one can see, the different variants occur within the middle of the assembly diagram, thus leading to multiple variations of the products occurring early on. We have modified the assembly diagram to delay product differentiation, as this will reduce lead time in creating different products. The jar and blade variants are incorporated almost at the end of the assembly process, overall simplifying the manufacturing process. Note that one of the jar variant will not include a filler cap and lid. That concludes our presentation. Thank you for listening.